In this video, we will build a background removal application using deep learning in the TensorFlow framework. Hello friends, welcome to this video. This is Nikhil Tomar and you are watching Idiot Developer. Make sure to subscribe the channel and hit that bell icon for more such videos on deep learning. The video is divided into parts. In the first part, we are going to design the architecture for the binary segmentation task. So here in this application, we are going to give a test image to the model, and the model is going to predict the mask. And with the help of that mask, we gonna know where the human lies. And with the help of that, we are going to remove the background. In the next part, we are going to train the architecture on the people segmentation dataset. And at the last part, we are going to make prediction on test images. Now let me just give you an overview about the dataset. So this is the name of the dataset, that is people underscore segmentation. And if you see, it contain near about 5,000 samples. It's taking a bit of time. If you look at the corner, here you can see 5,678 samples it contains. So this is the size of our dataset. So in the images folder, we have images, and in the mask folder, we have mask. So we're going to use this dataset to train our architecture. Now let's start with the model part. So first of all, we are going to import all the layers which we require for this task. And here if you see, we have imported this ResNet 50 architecture. So for our application, we are going to use a pre-trained encoder. That is, we're going to use a ResNet 50 as the encoder for better performance. Because if you have architecture which is where the encoder is built from scratch, it can also give good performance, but it's gonna take time. So using a pre-trained encoder gives you better performance in less time. So a pre-trained encoder helps the model to converge much faster, at a much faster rate. Okay. And one more application, like I haven't tested, but this is my theory. Like if your data set is less, let's say you have less images, so what you can do, you can freeze the this ResNet 50 part and just train the decoder part. If your data set is more of a natural data set, so in that case, the freezing the ResNet 50 is also a good option. Maybe you can try that, and if it works, then it's nice. Now let's build some blocks first. First of all, we're gonna have a simple residual block. We can say residual block. So it's gonna take the input feature map and the number of filters. Okay. Now let's start with some layers. So first we have our convolution layer, then a batch normalization, and then a relu activation. Okay. Let's build the next set of layer. After that, we have the convolution layer, then a batch normalization layer, and both of these convolution layer would have the same number of output filters. Okay, so this is one part of the network where it take input and then it takes subsequent output from each layer. Now after that, we're gonna have one more set of layers, that is convolution and batch normalization, and this is going to be one by one convolution, and it takes the input, not the x. Okay, so you can see the name of the different variable x. So x refers to the main branch and s refers to the shortcut branch. Okay, now what we're gonna do, we're gonna add both the x and the s and pass it through the relu activation function. So this is our simple residual block. Now we're gonna give the output of relu activation function as the output of this residual block. So this is really simple, just a residual block, because it helps to deepen the network. And also our ResNet 50 is also built using the residual block. Now next, we're gonna have a dilated convolution. So the dilated convolution basically increases the field of view of your convolution layers, which helps in like having a better feature representation, because now they can see a wide range of features as compared to a normal convolution, which further improves your performance in theory and also in practical part. I've seen this. So dilated convolution are like a must if you are working on any like object detection, especially in segmentation. From my experience, I can say the dilated part really helps, is especially in those part where you have like where your mask can be of smaller, larger size. In that case, dilated convolution really helps. So this is our first set of layer where we have convolution, Bayes normalization, and a ReLU activation. If you see in the first layer, we have a dilation rate of 3, and now we have two more set of dilated convolution layer where we have increased the dilation rate to 6 and then 9. So if you see, we have x1, x2, and x3. Now we're going to concatenate them. So we have concatenated them here. Now next, we're going to have few sets of layer where we have applied a one by one convolution, that is a pointwise convolution. So the reason for applying the pointwise convolution here is to decrease the number of filters to num filters, because if you see, we have concatenate these layers, the number of filters increased 3 times. So to decrease that, we have applied a one by one convolution. Now we're going to give x as the output of this dilated convolution. Okay, now let's start with the build model. Start building our model. So this is name the function build model. So it's going to take the input shape. Now first of all, we need to define our input layer. Let's also define our main function, that is this Python's line if name equals to main. From here we'll begin the execution. So we're going to have our input shape, and the shape of the input would be 512 by 512, and then we're going to have input as RGB. Now we're going to call our build model function, give it the input shape. Yeah, now we're going to run the model and check the input layer shape. Okay, let's see the shape of the input layer. So here I've already activated my TensorFlow environment. So let me just show you the version. So I'm using Python 3.10, and now I'm going to show you the version of TensorFlow which I am using. So let's import. So it is imported. Now the version, so that we know which version of TensorFlow I'm. So I'm using 2.9.1. I don't know whether it is old or updated, but it's working fine for me. So I'm not updating anything for now, because I don't want to mess up with the CUDA files and every other thing. It's like the CUDA and everything give a lot of headache, but I think now they made it much simpler. Okay, let's come back to our model part. Let's execute it. Okay, so you can see this is our input layer. So none refers to basically the batch size. That is none for now. But the training time it would be defined. We're going to define it. Here the height and width you can see 512 by 512, and input is an RGB image. So till now the input layer is fine. Now what are we going to do? We're going to import our pre-trained ResNet 50 model. Okay, so we have defined this ResNet 50. Here we say include top equals to false, because we want the feature extractor part, not the image classification part. Then we say weights is equals to ImageNet, because we want to load the weights here, because we want a pre-trained ResNet 50, not in a ResNet 50 from scratch. Even I think ResNet 50 from scratch would also be good, but having weights initialized would be better than some random weights. Then the input to this ResNet 50 would be inputs here. Now let me just print its summary, because what we need to do, we need to extract some layers from this architecture, this ResNet 50. So if you see all these layers, now I'll tell you from here. Let me go just to the top. Okay, you see these are the layer names. So what we need the layer name. Okay, so because we are following a sequential encoder decoder part. Let's say we at the end, let's say our feature map size is, let's say 16 by 16. So we're going to upsample it by factor of 2. So it became 32. Then we concatenate it with the which in the skip connection of the 32 by 32, then 64 by 64, then 128, then 256, and 500. So like this. So we need to extract the name of the layer so that we can get those specific skip connection features from this ResNet 50. First is 512 by 512. If you see, only the input layer have this shape. After that we don't have that shape. So first would be this input one, then like this you can go for 256 now. So this would be cone one ReLU would be skip connection, another skip connection. You see, because after that there is no shape matching 256. So skip connection, what I mostly prefer is the output of a ReLU activation function, which I mostly prefer as a skip connection, are much better. So like this, we're gonna have 5 skip connection from here. So what I'll do, I'll just directly copy paste them here. Okay, you can simply follow the thing which I am doing. So this is the method to extract those skip connections. So first I say S1, the name of the architecture, then you say get layer, the name of the layer, then dot output. So this method works only for TensorFlow. In PyTorch things are really different. Like even I get confused with PyTorch, but this TensorFlow and Keras thing, extracting intermediate feature map, is really easy. It's much efficient than PyTorch. Maybe because I haven't understand it, that's why I'm saying PyTorch is not that efficient. Maybe that is a good reason. So like this we have S2, S3, S4, and S5. So now what I'll do, I'll just print the shape from S1 to S5. So let me just run this program. Okay, if you see, first shape is 512 by 512, then 256, then 128, then 64, and then 32. So we are done with the encoder part for now. If you see, now what we need is a bridge. So in encoder, in between encoder and decoder, we have a bridge. Okay. So for bridge, we are going to use our dilated convolution. If you see, we have built this function here, dilated convolution layer. Let's use this as the bridge. Okay, so we're gonna say B1 equals to dilated con. Input would be S5 and number of output features, let's say 1024. Now let me print the shape of B1, and it should be of height and width 32 by 32, and number of output channels should be 1024. You see, the exact same shape as I predicted. Like while working on the architecture part, so just follow the shape also, so that you know which shape to add, which shape won't add. These are the things which cause issues while running your program. Okay, so now after that, what we need to build a decoder. So we're going to build our decoder block. So let's say decoder here, and we're going to build our decoder part. So let us define the name of a function called decoder. So what this decoder function would take, it takes 3 inputs, 3 argument. First would be your main input, second would be a skip connection feature map, and third would be number of filters. So first of all, we are going to upsample the main feature map, that is the inputs argument, using a bilinear interpolation, and we're going to increase it by a factor of 2. Then we're going to concatenate the feature map with the skip connection, and these skip connection are from the encoder. So we get the information from encoder, concatenate them, and then pass through a residual block. If you see, input would be X, that is concatenated input, and number of filters. So now our decoder block is also done. So let's start building the decoder part. So we're going to say D1 equals to decoder block, then input would be B1 and a skip connection. Okay, skip connection would be S4. If you see, why not S5? See, the size of S5 is 32 by 32. We're going to upsample it when it passes through the decoder by factor of 2, it became 64. Now when you want to concatenate a feature of height and width 64 by 64, so the another feature map should also have the shape of 64 by 64, and S4 have that exact shape. S4. Now number of filters would be 512, so we're going to decrease them. Okay, now like this we're going to have D2, D3 and D4. D2, D3, D4. So now what I'll do, I'll print the shape of each of one, D1, D2, D3, D3, D4. Okay, so we're done with till D4 only we have. Let's run the program. Okay, you can see first is 64 by 64, then 128 by 128, then 256 by 256, and at last we have a feature map of height and width same as the input image. So now there are two ways to work here. Okay, I will go for both of them. What you can do, you can just take the output of D4 and pass it through a 1 by 1 convolution with 1 as the feature map, and you get the mask. But here we're going to follow the deep supervision way. So what I'll do, I'll first upsample D1 equals to 512, 512. So D1 is, you see, it's 64, I think, if I remember. Yeah, so 64 into, if I do it 2 times and it became 128, then 4 times came 256. Yeah, so we should upsample it by factor of 8, and then I'm going to pass it through a convolution layer, that is a 1 by 1 con. So now y1 would also be equals to 512. Let me just print it, so you know. So this is kind of deep supervision I am using here, because deep supervision really helps. You can see 512 by 512 and mask this one. This is also fine. Like this we have y2, y3 and y4. So y2 increase by factor of 4, then a 1 by 1 convolution, then y3 increase by factor of 2 by 2, and y3, then y4. So we have 4 different output here. Now what are we going to do? We're going to concatenate all of them as one. So it is easy for us to train. That is why I will concatenate multiple output as one, and then we're going to build our model, because now we have the input. Go to the top, this input layer we have and the output layer we have. When you have both these things, it's time to build the model. So we have built our model. Now let's print its summary. Let's run this program and see if there's any error. Okay, so it's working fine. And at last, if you see 512 by 512 by 4, because we have 4 different masks and the main mask. Okay, out of these 4 would be this 4th one, the last one would be our main mask, because that is going to be the really fine mask. Rest all first, second, third would not be that much fine. They would be just okay. They are just used for training. They are not going to be used as a testing time or the prediction time. Okay, so this is the architecture part. Now we're going to move on to the training part. Let's move on to the training. And first of all, what we're going to do, we're going to import all the libraries which we need. First is this OS library. Then we define this os.environment and then this variable value to 2. So if you have seen this entire thing, you see every time we run the program, we have these statements. So we don't need these line every time. So just tell you what your GPU is, every other some messages. We don't need them. So to get rid of those, we have run this line. We have put this line here. Then we have NumPy for numerical calculation. Then we have pandas. I think we don't need pandas. We'll remove them later. Then we have OpenCV to read and write or resize the images and mask. Then we have Globe to extract all the images and mask from the folders. Then we have SciPy. Then we have sklearn. From there we import train test split to split the dataset. Then we have imported TensorFlow. After that we have imported callbacks. I think we have 4 callbacks. Model checkpoint to save the weight file. This is to decrease the learning rate. This is to stop the training. And the last one, CSV logger, is to log all the training loss, learning rate, validation loss into a CSV file. And then from our model file, we have also imported the build model. Okay. After that, we are done with the import part. Next, what we're going to do, we're going to have two global variable, that is image height and image width. Okay, because we're going to use them in some function, so it is better to define at the top. Next, we're going to have a function to create the folders, because sometimes we want to create some folders and I do not want to manually create folder. It would be better if the program automatically create a folder accordingly, because program can also check if that folder exists, then you don't need to create that folder. If it does not exist, then create that folder. So this is how this function works. So it takes the path, then it checks. If not, okay, if this path does not exist, then create that path or that folder. See, that is really easy. Now our next part would be splitting of the data set into training and validation. So I'll just write the entire function here and then explain each and every line. So the name of the function is load underscore data set. It's going to take the path, and that path would be this people's segmentation. So it can be different on your system, okay, and it's different on my system also. So first, what we do, we extract all the images in mask. So what we do, we first have this our path. Okay, this is the path. So we use os.path.join. Then we specify the main path of the dataset, then images folder, and from images folder we have specified this pattern, that is star.jpg. This means star refers to anything. It can start with anything, but it should end with .jpg. And same if you see with mask, we have just changed the folder name to mask, then say star.png. And this pattern, path pattern, is given to the globe, and it extracts all the images and mask with their corresponding extension, that is .jpg and .png. And then this globe give us lists, so we sort those lists. Okay, like here the sorting is really important. Let's say if we don't sort, the first globe would give us a list of the images path. So let's say in the first position or the 0th index position, it have a file name 1.jpg, but in the globe it can begin with 2.jpg or 5.jpg, like, because it's random. So to specify, because both the image and mask folder have same name, so when you sort them, so you have both pair of images and mask at the same index position. So that is why we sort it here. So sorting is really important, because if you don't sort, you're going to have different pair of image and mask and your training won't work. And the best thing is that you won't get any error, but the performance would drop. So just remember to sort them. First manually check them. Just check 2, 3 file path, and if they are okay, then rest of them is also okay. So till here we have loaded both image and mask. Okay, now we split it. So we have split a ratio of 0.1. So we split them in 90:10 ratio. So 90% of the data would be used for training and 10% would be used for validation. So that is what we have done. So we have given a split size. So how much would be 10% or the 1% of this total? Then we split it here, and then we here have training and validation. Now let's begin with the main function. First of all, we're going to seed the environment. That is really important in any deep learning for reproducibility. And after that, we're going to create a folder or a directory to store our weight files in the CSV file that would be created. Next, we're going to define some set of hyperparameters. So here we have defined the height and width as 512 by 512. This is the input shape, then a batch size of 4, a learning rate of 1e-4, and 100 epoch. Definitely, we are not going to run it on 100 epoch. I've trained this model already on like 5 to 6 epochs, and I think that give you good performance. You can train the model for more epochs for better performance. Now let's have some paths. So first we have the dataset path. Okay, this is the path for our dataset, that is people segmentation. You can download the dataset from the link given in the description. Next we have the model path where our weight file would be saved. Then we have CSV path where our this CSV file would be saved. Next we're going to load our dataset. So we have called the load dataset function with the dataset path, and here we change the split to 0.2%. Like the 0.1 is the default value. If you don't provide anything, it would have a default value of 0.1. Now here we divide the dataset into 80-20 because we have changed the split to 0.2. Now let's just run the program for now. Python 3. Okay. Now if I show you the folder, if you see, it does not have any folder here with the name of files. Now if I run this, okay, you see we have a files folder here, and this is created by the Python automatically. We don't need to create any folder. I am going to remove it for now, and here you can see the 80-20 split. So 80% of the total images are 4543 images in mask pair, and the 20% is 1135 images in mask pair. Okay, so we are done with the dataset part. Now we need to work on the dataset pipeline. That is, we're going to read the image, and that is going to be used by the model during training. So that data pipeline part we need to work upon. So first of all, we're going to define two simple functions. First to read the image, and second to read the mask. I'm going to copy them here and then explain each line. So the name of the function is read_image. It takes your path. So our next line is path.decode. So all these strings would be encoded because this function is going to be used by the TensorFlow, and there the path is going to be encoded. So we first decode it. We get the normal string, the path. Then we use OpenCV to read our image as RGB. Then we resize it, and we normalize all the pixels in the range of 0 and 1 by dividing them with 255. So 255 is the maximum pixel value an RGB image can have. Then we convert it to float 32. So we explicitly say here, because we want to, we would require what is the output data type of this function. And same we have for the mask, same lines of code, just few changes. So here also in the read mask function, we first decode the path, then we read the image as not RGB at the grayscale because it's a mask, so it would be grayscale. Then we resize this mask, then we explicitly define its data type, that is float 32. If you see, we don't normalize the mask here because the mask pixel value are already 0 and 1. So 0 refers to background and 1 refers to human. That is why we don't normalize them. So if your masks are black and white, let's say your main class is white, this means white pixel denotes 255. So you need to divide that with 255 to normalize the mask pixel. So the output of like each pixel in the mask should be either 0 or 1 because it's a binary segmentation. Then we increase its dimension on the last axis and we concatenate it 4 times. So here what it would done. So I'll show you what it would be like. Say height by width by 1. Oh no, not 1. This would be height by width. It's like in this shape. And here it would be like we add a dimension at the last. Because if you remember our architecture, it has 4 masks. It's based on deep supervision, and we have concatenated them. So during training, we also need same shape of output. So it would be 4 now because we have concatenated it 4 times on the last axis, and we give it as the output. So these two functions are done. Now we have one more function, that is tf_parse, which uses both these functions. So this is the function tf_parse. It take x and y. So here x and y refers to individual image and mask path. Okay, here both x and y refers to in this _parse functions also. So its execution would begin from here. to execute this numpy function. So in the TensorFlow, if you want to use anything outside the TensorFlow, let's say you want to use some numpy function, OpenCV function, you call this TensorFlow function, and inside this you need to call the function which you want to execute. And here we want to execute this underscore parse. It take two input x and y, and it first read the image and read the mask and give you both image and mask. So here in this numpy function, you give the name of the function, input to the function, and the output data type of the function, and it's gonna give you x and y. Here we need to set the shape of x and y. So x would be image height, image width, and because it's RGB, so we have specified 3 here. For the mask, same height and width, just number of channels would be 4. You see why? Now we know why for, because it's deep supervision. Now we are on the last function to build our dataset pipeline. So here we have another function, tf underscore dataset. So here we use a tf.data API. Okay, and this is much more efficient, like when you don't have greater, like it's called the system GPU RAM, GPU memory. Okay, so you can specify this pre-batch also according to, okay, let's go from sequence. So first tf.data.dataset from tensor slices. Here you can see it take x and y. So these x and y refer to the list of image and path, not individual, just list of image and mask path. Then it uses this tf parse function. So what it does, it convert everything into tensor. Then you create a batch and then say prefetch. So prefetch, what it basically does, let's say your first batch is in training, then while the first batch is involved with training, it fetch next 10 batches. So it carry forward 10 batches in a sequence, so that the system need not to wait to load the data. Okay, you can decrease this value, or you can set it to auto tune, or you can remove it, even it won't affect. Okay, so this is our tf data pipeline. Now let's go down and write the code for the dataset pipeline. It's really simple. You just need to use this tf data function. Above it's really complex. You have 4 functions, I think, but here it's really simple. It's train dataset. You provide train x, train y, and batch size. Then we have valid images, valid mask, and batch size. We are done. Now we're gonna work on our model. We're gonna compile it. So this is our model, and here we're gonna use loss as the binary cross entropy, and optimizer would be Adam, and learning rate we have already specified. Now we're gonna begin with the training. Before training, we need to specify our callbacks. So those callbacks are important. So we have 4 callbacks. So first is model checkpoint, and this callback would help us to save the weight file. So what it does, it just monitor your validation loss. We can also specify, if don't specify, by default you take valid loss. So if your validation loss decreases, then only it's going to save the weight file. If your validation loss increases, this means performance is not getting better, then it won't save your weight file. Next we have reduce LR on plateau. So this also check your one of the metrics, that is the validation loss. And let's say for continuous of 5 epoch, your loss does not decrease, that is validation loss is going to decrease the learning rate by factor of 0.1. Next we have CSV logger. So it's going to create a CSV file and save your training loss, training learning rate, and all the matrices which are involved during training. And at last we have early stopping. So this is our mechanism to stop the training. So let's say your validation loss does not decrease for a continuous of 20 epoch, so it's going to stop the training. So these are the callbacks. So these callbacks are really important. Okay, don't just take them for granted. You can remove them, check the performance, and add them and check the, there would be like huge difference. And at last we have called our model.fit line. This is really essential. This is the last line which would begin the training. Okay, we have some indentation error. Okay, here this is because I directly copy pasted. Okay, now it's gonna begin with the training. So I'll show you how the training is if we have any error. So I'm using an RTX 3090, okay, and I have my GPU has a 24 GB memory. So I can run the model on this high size with the batch size of 4. Maybe you can decrease it for yourself. You can use 256 by 256, such a set batch size accordingly, okay. Maybe you would encounter an out of memory error. For that, please decrease this, what do you say, the input size of the image, okay. You can also decrease the batch size. There are multiple things you can do. You can also decrease the number of parameter in the model, okay. So these are the things which you need to work upon yourself, because on my system it's working fine, on your it may not. So this is the training how it's going to follow. I've already trained the model on few epochs, and I'm going to show you the weight file and the CSV file. So this is the files folder, and here you see we have two files, data.csv and model.h5. So this model.h5 is our trained weight file, and we have trained it for, I think, yeah, 8 epoch. We have trained it for 8 epoch, and if you see for 8, within 8 epoch our training loss decreases from 0.15 to 0.3, and validation loss decrease from 0.12 to 0.11. So this is good. Within 8 epoch, I believe the performance is good. You don't need to do anything else. Error. Now we need to work upon the prediction part. Okay, prediction is important because this is where our main application is. This is the main application. Because rest two things are like, okay, you need to do, but now we're gonna enjoy the prediction part. Okay, let's import all the functions and every other thing. Okay, so these are the libraries which we're going to require for our prediction. Next, we're going to define the two global parameter, that is height and width. So we have defined them at the top. Technically they are not global variable, we need to write globe and then, but they're gonna work. Okay, so we need some test images, okay, so to test those. So I've already downloaded some test samples, okay, and I'll show you where it is. Okay, here you see I have this test folder, inside it I have images. So these are few test samples. Just also take a look at their sizes, how high resolution images they are. Okay, I'll show you next sample. See, so we have different kind of samples from different view angle. So we have child, we have different backgrounds also. So we're going to check the performance, and if you see, this is our model is mostly trained where images have one human. Okay, now we have this sample which have more than one human, so we're going to check it how it works. So you can see the image is really huge. Okay, so you need to resize your mark to those sizes to work. Okay, let's close these samples, and we're gonna save our mask and remove the background. So we're gonna call our main function, and we're gonna build a folder where we're gonna save our mask. Where we have seed the environment, we have created a folder in the test folder, and we have the name of the folder would be masks. That would store your mask and also how the image would look. Now we need to load our model. So we have simply loaded the model using tf.keras.models, then load model, and then name of the weight file, the path to the weight file. Now we're going to load the summary of the this model. The summary, if it is shown on the terminal, this means a model is fine. We have successfully loaded the model. Okay, so till this part it's fine. Now we're going to load the test images. We're going to load the test data set. So again, globe test images star. So star means load everything. This time we have not sort the list because it's just images, not the mask. Okay, so now we're going to loop over this list. So we have path in TQDM, this data access list, then total, how many iteration we need to do. We need to specify in the TQDM this total. Now what I'll do, I'll just print the path, because we need to do some operations here on the path, as we need to extract the name from this path. Okay, if you see, this is the path for me. So I am using an Linux based operating system, so here the slash is different. But in your system, if you are using especially Windows, guys, these slashes would be different. I think they would be these. I think these work for you. So just please have a look at those slashes first. That is why I'm showing this path. Otherwise I need not to show, everything would be fine. But at this step you would have error, and you would always like may have problem, not always, but from my experience, I have experience, guys, where they are not able to load the images, or they are not able to save the mask because of those slashes and the difference between the Linux and the Windows environment. Okay, just please take care of that thing. Now first of all, what we're gonna do, we need to extract the name from this path. Okay, this we require just this name, not even that extension. So let's see, name path, we're gonna split this path on the basis of the slash. Now here you need to carefully check what slash is. This is not about, this is the pattern on which we're gonna split it, because if you see, all the folder name are separated by the slash. So what we simply do, we simply put the slash, and this would split the name, split the string into a list. So we have saved this. Now let's run this. Okay, we have indentation error. Okay, yeah, some indentation error we have. So now let's do it again. Hope it would work. Yeah, it has taken time, but it did work. Now if you just compare this with this list, so it has removed all the slashes, but I've created a list. We have test as once item in the list, then images, then complete name. Now whatever your path would be, the name would always be in the last. What we can say, we can simply say -1. Now run it again, you would get this string photo15 and something .jpg. See, now again you're gonna split it on the base of dot. If you got this thing till now, it's fine. Now next would be same for every operating system. You're gonna say dot, you're gonna split it again. Now you're gonna have two items, first is name and then the extension. Now you can extract the name from the 0th index position. So there can be any other way to extract the name, it depends, but this is my way of extracting the name. You can see we have extracted the name. Now let's move forward. So now we're going to read the image and make it in a proper format so that we can give it as an input to the model. So this is our image, the path. We have read this image using OpenCV, and we have reading it as an RGB. So we need to follow the same same protocols for reading the image as we are doing while training, because model is trained with these output. The output look at the end like this. So if you see, we read the image, we resize, then we normalize. These three steps are important, because you cannot change the image size, or you cannot like say I don't want to normalize it now. You have to follow those same steps. This is image, this is original image. So we have saved the height and width the original image, then we resize it. Okay, then here we say x divided by 255, so we normalize it, then we convert it to float 32, and then we say, then we expand its dimension on the last axis. Let me explain here what happens. So we have height, width, and number of channels 3. So this is fine till now, because our deep learning model usually take input in the form of batches, and here we only have one image. So we extend its dimension on first axis, that is 0th axis. So it became, so this is how it became. It's a batch size of one image only. So our mask would also be a mask of one batch only. So now we need to make prediction. So what we do, we're going to say y model dot predict, access the input, verbose equals to 0. Okay, now I'll print the shape of y. Okay, if you see, it also is a batch of one item only, and our one output contain 4 masks, one main mask and rest we can ignore. Okay, so what we'll do, we'll say 0 here. Now we have 4 masks. So okay, so our main mask would be like, if you want to just work on the main mask, so from here if you say 0, that would be first and second mask, then third mask, and this would be fourth mask. So what we'll do, we'll save each mask individually. I just save one mask and then we'll work on the final mask only. For I in range, so we know the 4 masks, we are done 4. Now we're going to say y equals to y. This would be first height, we don't want to do anything, width, then y. Now I'm going to print the shape of y. It should be 512 by 512. Okay, there's some mistake. Yeah, you need not to say it y, because again it's going to be y here. Should can say mask. Oh, this would work. Yeah, I realized this mistake. Okay, let's just wait. Yeah, this time you can see it's really working fine. So we have our 4 masks. Now what we're gonna do, we're gonna save each of them. Let's say cb2 dot I am right. Okay, first you need to specify the path. So we're gonna say test masks. You remember the path here, masks. In this we're gonna save our mask. So next we're gonna say name underscore I dot png, and now we're gonna say mask. Because these masks are normalized in the range of 0 and 1, we're gonna multiply them with 255. Now we're gonna run this and check how our 4 masks look. All the 4 masks, how they look. Okay, so we are in our mask. So this is our first, second, third, and fourth. So this is our final. All the 4 masks look kind of much similar to each other. That can happen. Okay, so this is how. Now you have just imagine you have 4 masks. You can do any kind of pre-processing. You can do anything. Okay, and you can work with them. But I'm gonna use this last one. Okay, so I'm gonna remove this folder from here. Okay, so now let's work on this part. I'm going to remove this part, and we're gonna here say -1. Okay, the last mask we want. So next we're gonna resize it. You see, it's of size 512 by 512. So you want to remove background from the image. We need to resize this mask. Resize y, then the height and width from the original image. So while resizing, first provide the width, then height. Then we're gonna expand its dimension y on the last axis. Next we're gonna save our image. Save the image, we can see. Okay, so first would be our masked image is equals to image. We're gonna multiply it with y. Fine. Now we can simply save it. test slash mask slash name dot png, and we can say masked. Now I'll explain this simple operation again, okay, because this seems simple, bit of tricky can be. So this is our image and this is our mask. So our mask is in the range of 0 and 1. Okay, it's not exactly 0 or 1, it's in the range of 0 and 1. So don't apply any thresholding, especially in this background day. It's not gonna give you best performance. Only this row values between 0 and 1, kind of 0 0.1, 0 0.5, 0.25, 0.78, 0.92 gonna work fine for you. Okay, so what we do, we simply multiply those values with this. So those values which are more close to 0, or background would have a pixel value 0. So when 0 multiply anything, it became 0. So that area would appear as black 0, and rest area would get multiplied accordingly. Okay, so the mask, so the main area, main class would be 1, or the border areas would be near about between 0 and 1, or these kind of smaller values they have. So when you multiply them, they work accordingly. So what I'll do, I'll just remove this break line from here, and I'm going to run this entire code on all the images. It's working. It's a bit slow because we are resizing and multiplying. Okay, if you see the performance, okay, if you see, just only human is visible. Just these border areas are not that good. Okay, if you see this example, it's also working fine with more than one human. So it's working fine. If you see, it's removing background really well. So if you want really good performance, really, so you need to train it on more data set for more epoch. Okay, see, 4 humans and it's working fine. Still, it's trained on images where we have 1 human, but it's working. That is the advantage of deep learning. It's work well. Even sample is not there in test set. Now what we're gonna do? We're gonna concatenate the original image also. So what we have done? We have concatenated the original image. Have a simple gray line in between image and mask to separate them. Let's run this program again, and we're gonna let it run. So we have reached the end part of the video. If you still are there and watching this part, I'm really thankful to you. I hope you have learned something and you can use this new knowledge in some of your project or anywhere, which it's just that you should learn something, you get some knowledge from here. If you enjoyed it, then please make sure to like the video, share it with your friend, and also subscribe the channel. And if you have any query, then please write it down or message me. I'll try to solve your query or answer you if possible, because see, even I am a human. If you all gonna message me, I'm not, I cannot reply to all, but I'm gonna reply to some people. And you can also join the group. I have the please check the link for the Telegram group in the description. Do join the group, please. It would be really helpful, because there you can talk with each other. Each of you people can solve each of your query, because I alone, single human, cannot solve all your query. So this done. Now you can easily compare. You can see original image, a fine line, you see the gray line separating image and mask, and this image where background is removed. See, some areas are not working here. If you see, it's fine. Even the space between the legs is also removed. Some border is also okay. I believe if you train it more, it's going to give you better performance. I believe. I truly believe it would work. So it's working really well because we haven't trained it much. It's a simpler network with deep supervision. I think deep supervision also help. Okay, you see, I'm like, this is really good. See if this, okay, this is because this background is black, so it's, you cannot, but the image looks really well. But if you see, problem is that it also segmenting this flamingo kind of this. You cannot see this object also as the human, because it's not a part of our data set. because our data set contain one human and it's not one, it's more than one. So there it can do some here and there, but it's working fine. I'm really liking these images. So I hope you learned something and you enjoyed this video. So again, I'm gonna say like the video, share the video friends, and do subscribe the channel. So at the end, thank you and a happy new year.